Good afternoon. My name is Dr. Ann Fitzpatrick, and I'm with the National Security Agency, and I'm here to talk to you for a little bit this afternoon about cybersecurity for future extreme computing. I appreciate your taking a little time out of your day to spend to listen to my presentation and chat a little bit. And I'd like to take about 40 minutes or so to talk about this subject. This is not going to be, I'm going to go to my first slide. This is not going to be a really detailed technical talk, but more from a big picture and policy perspective. And when I talk about cybersecurity, I'm going to talk about it in many levels. To some degree today, a little bit about what I'd call like traditional hacking and things like this, but also from a big picture perspective as to what cybersecurity means in a globalized world, and from high-end computing, which I'll get into the definition of in a little bit, but where we need to be as a nation and where we need to be as to be economically competitive and going forward in high tech. So it's a big topic, it's a very broad topic. But what I'd like to start off with the slide you see right now, I have several goals for this presentation I'd like you to take away from this. I'm going to go into some brief history of high-end computing, and I'll talk about my terms of what this means in a minute, and the current state of the field, where we're at. And I want you, I'm not an high performance computing or HPC engineer, scientist, mathematician, or designer. I'm a tech savvy social scientist, and I'll talk to my background in a minute. But part of what my job is, and part of what I've done for my career, is get people to question their assumptions about things, and especially when designing machinery or big computers or things like this. And I'm going to describe what's happening. What I've seen ever working for 26 years in this field, what I see is some serious paradigm shifts happening underway in high performance computing. And we're also in kind of a Clay Christensen innovator's dilemma scenario, I see, and why that's seen maybe as a crisis, but also as an opportunity. And I'm going to talk to that a little later today. And I'd kind of like you to try to see this with me. And then I'm going to talk a little bit about cybersecurity in a big picture sense for high performance computing futures and where we might go from there. So I'm trying to get you to think and get you to question your assumptions and talk about big impact. I want to kick off a long-term discussion and encourage people to challenge their assumptions about where we are. And I'll talk to some of these specific things a little later on. And just going with the assumption here that advanced computing, if you really think about it, in various forms has become kind of an invisible but critical technological backbone for modern society today. I mean, who could not live without having their laptop or PC or phone, or, you think about it, your car has something like 50 or plus CPUs. In fact, there's a chip shortage going on right now. I'll speak to that a little later, where the auto manufacturers are slowing production. You can't get away from this today. It's really hard to. And then I'll talk a little bit about what's called the top 500 list, which is the top 500 ranking of supercomputers in the world, and how we've come historically, and that what that has been, how that got developed, and question whether it matters anymore. And you'll see more later in the talk why. Just a little bit about me. This is my first time speaking at RSA. I've not normally run with this crowd before, because I normally run with the supercomputing or SC group, which is a big meeting like RSA that meets every November normally, when we weren't having COVID. And it's a lot of the high performance computing scientific community, a lot of the US national labs and people from academia and people from some industry. It's not so cybersecurity focused, but I think it's becoming more so, I've observed, which is a good thing. And I have a degree in science and technology studies from Virginia Tech. What is science and technology studies, you might ask? I get asked this question a lot. It's known colloquially as STS. It's an interdisciplinary field that teaches people both social science and hard science. My PhD professor was a philosopher of science. There is such a field. And it's a really cool set of skills to have, because it leads you to be able to talk between the scientists and engineers and the policymakers, such as like in Washington, DC, and translate the language between them. I've made kind of a career of that, and it's been a lot of fun. So, and again, I'm at the latter part of my career these days, but I've spent time working in academia. I was Los Alamos National Laboratory staff. I have a couple of books, and I made my way to Washington, D.C. about 15 years ago, and worked at a number of government agencies, including the Department of Energy, Department of Defense, Department of Homeland Security, and made my way to NSA last year. And it's been a lot of fun. And so, again, because of my background and because of what I've done, things I research, I tend to think of security in terms of how to protect the US from cyber enemies and how to protect our technological and competitive advantages. It's part of my job. So with that, we will move to the next slide, get into some history here. So what is high performance computing? And let me define these terms. Extreme computing or high performance computing, supercomputing, HPC, we call it for short. For our purposes today, they're all the same thing, essentially. In the business, we tend to call it all HPC. But extreme, you might, surmise that it's like high end or computing that is designed to do very big and complicated problem set. And that's right, that's the right assumption. But I want to talk a little bit about history. I always believe that we can learn lessons from history, and that kind of can see what's happened in the past and see what's happening now, and maybe take some lessons from that. So what is HPC? Some of you probably this crowd knows for the most part, but some of you may not. It's a very specific, very rarefied kind of high-end part of the information technology field that is tends to lend itself to being used for really big science problems, modeling nuclear weapons, modeling cryptanalysis, things like studying the universe and the way that the sun burns, for example, or people who study black holes, extreme weather, things like this. And it was conceived during World War II to help win the war. And back in the 1940s, when World War II commenced, IBM presented these mechanical tabulators, and they had these things called punch cards. And some of you are old enough to remember these. I used them when I was early in my career. They're a little card this big, and you would feed them to the machine, and that's how you would do your computations. But things have changed drastically. But there would be these rooms full of these devices, and rooms full of mostly women, so-called hand computers. That was a device that looked like a big typewriter, and they would calculate arms trajectories through the war and towards the end of the war. To when you fired a weapon, the trajectory had to be very precise, and they were used to figure out later on the atomic bomb design. And so that latter problem set is a very hard problem set, and drew some of the West's most prominent scientists to Los Alamos, New Mexico, where the atomic bomb project was carried out in secret. And so many European scientists who were of Jewish extraction had to flee Europe when Hitler arose in the 1930s. Many came to America, including Albert Einstein. Among them was also the Hungarian John von Neumann. These were just amazingly brilliant people. I was fascinated with them when I was a graduate student, and I actually got to meet some of their colleagues when I worked at Los Alamos in the early 90s as a student. And but John von Neumann is interesting because he's largely credited with inventing the first modern electronic computer, the Electronic Numeric Integrator and Calculator, or ENIAC. It was at the University of Pennsylvania during World War II. And ENIAC was supposed to be, and it was used for conventional armaments trajectories that they would practice at Aberdeen, Maryland, at the Army proving grounds. And so von Neumann, though, figured out how to employ it to do some calculations for the first atomic bomb. And he and a lot of his again, women programmers figured out how to do this, and they saved a lot of precious time, and it resulted in Fat Man and Little Boy and the bombing of Hiroshima and Nagasaki. They calculated how those things would work, and it really resulted in not having to send the U.S. Marines to invade Japan in 1945. And while the ethical matter of the atomic bombing and of Japan is beyond the scope of this talk, World War II, as the scientists who I met there told me it was a different time, and people felt it was a desperate war. So I'm happy, if anyone wants to talk about this offline, I did my PhD thesis on the atomic bomb and computing about this subject, and so a long time ago. But if anyone wants to talk about it after my presentation or on email or anything, I'm very happy to do that. But moving on. Likewise, and pictured up in the top corner here, would be my top left corner. Again, the British were doing something similar in the UK. Alan Turing, he's pictured here, played by the actor Benedict Cumberbatch in The Imitation Game. He's working on the British rough equivalent of the ENIAC here, the bomb, that's bomb with an E. What it did, it allowed the British to break the German naval codes and allowed the Allies to get ahead of Germany in World War II. And so this was very groundbreaking technology for that time. And I wanted to kind of set the tone for this talk, and because it'll give us some perspective of where we've come in the last 70 to 75 years or so. But general, since in the other pictures I have here, these are other more contemporary things. There's the stock market and where are these machines used today, definitely for high-speed trading, for weather prediction, as you can see in the top right corner, helping us predict the path of hurricanes and things. Summit Computer in the middle, it's at Oak Ridge National Laboratory down in Tennessee. And why is there a Pringles can on here, you might ask? So the story behind that is other industry has adopted HPC, oil and gas, manufacturing. So Pringles used to be owned by Procter & Gamble Corporation. I don't believe they are anymore. But at the time, P&G had a HPC division, and they have to package their household products very fast, right? So they Pringles, if you have ever eaten them, they're shaped kind of like this. They're like a wing or a half wing, and the way they package these things, they're blown into the can very fast and with very much precision. Well, to do that at really high speeds and at volume, you need computer modeling, supercomputer modeling to do that, and that's what they do. And they would do the same thing with like spinning the toilet paper rolls and things like this. So it's gotten adopted by other things in science. Not so much the scale that you would do in the national labs and weapons modeling and Department of Defense applications and things, but people are trying to adopt these computers more in maybe smaller industries. It's been kind of a challenge. But the final thing I want to take away from this, I'd like you to take away from this slide is that HPC is a very specialized architecture compared to regular IT, your desktop or your laptop or something. And its programming is very specialized and very hard to do. One spends a lifetime learning to do this. And for many years, nuclear weapons design, things like intelligence cryptography needs drove the US supercomputing industry and it helped make the fortunes of companies like IBM and Cray. It really did. And over time, the machines kept increasing in speed and capability. And I'll talk to more detail on that in a little bit. And the big point is they were made in America. Their fact is this is no longer the case, it's going to haunt us for the most part and is hurting our cybersecurity. This is not the case anymore. They're not, the components, everything is not US made anymore. That's something to be concerned about. So we had no foreign competition either. So everything used to be US government driven, and that's not true anymore at all. I'll get into that more later. Again, gradual adoption by some industry, but not on the scale we'd probably like to see. But we'll talk about that. Let me go into the next slide. All right, so I think I need to also to set up the portion of this talk that is about cybersecurity. I want to talk a little more about what sets HPC, high performance computing, apart from other information tech. You might think, oh, it's just, a lot of computers wired together. Not exactly. HPC usually refers to the practice of aggregating computing power in a way that delivers much higher performance than one could get out of your typical desktop or workstation in order to solve big problems in science, engineering, sometimes business. It's a rarefied field and not a common profession. ask yourself, when was the last time you asked someone, what do you do for a living? And they say, I'm an HPC scientist, probably once in your life or something. It's a small field. It's a small community. Everybody knows one another. It's just the way it's evolved. There are various reasons for that. There's no one goes to college and gets a degree in high performance computing. It's not offered. You might get a computer science degree or engineering degree, but then often what happened to me, I got a fellowship to Los Alamos Lab in 1993, and I went out there to finish my PhD work and start learning some of this stuff. And often it's something you do, it's almost like you have to learn as an apprentice or on the job to do this kind of thing. And so people often spend 20 years trying to learn to program these kind of computers. It's very difficult. It's not, it's a very, you can't compare it to being a developer or something like this, or you can't go to GitHub and get the code. Stuff is still often programmed in Fortran, some C++, older languages that not a lot of younger people are going into today. And I'll talk to that sociology part of it a little later on and why that is and how that's changing the field. But these machines are optimized for high performance. You have to do this because often the scientific problem sets people are studying in astrophysics, you have to include things like changing times, multiple dimensions, changing densities that are happening in your material. And all this eats up memory, lots and lots of memory. Again, I think I mentioned if someone's studying a topic like how the sun burns, and it's really complicated stuff. And so it makes for, and because it's so difficult to do, it makes this HPC something of a closed community. And so it's kind of an exclusive club in some ways. And so that has affected the state of the field and ultimately security and where we're going forward. I have another slide on that topic a little later on. One thing HPC is differing, people often ask, well, how does it differ from cloud or data computing? Well, so HPCs actually need to sit physically close, kind of like pictured here, to one another to avoid lags in communication, the way that the problems are run. And so this is different from cloud, where servers can be vast different hundreds of miles or thousands of miles apart, it doesn't matter. HPCs often sport some types of exotic hardware. Yes, they do use conventional semiconductors produced all over the world, particularly in Asia, but things like special interconnect technologies have been developed for them so that the machines communicate with one another more easily. It's just the architecture is kind of specialized. And so software, again, Fortran, some C++, there's some stuff done in Linux and Unix to some degree. And then the other thing that makes HPC stand apart, they need extreme energy, they have extreme energy demands. Our next goal in HPC is to get to the exascale level. I'll talk to what that means in a few minutes, but the working exascale computer they're projecting is going to require anywhere from 20 to 65 megawatts of power annually. The cost to build is high too. Depending on the size of the machine, they can cost from 20 to 400 million to build one of these things. And so it's expensive. And then my last bullet here, I'm not going to read all the bullets, it's just not my style. You might think of HPC as a Ferrari on your desktop or laptops as a Toyota, and that the Toyota is more of a utilitarian thing for everyday use. The HPC is for very specialized and fast processing. So I've always liked that analogy. So next slide, slide 5. I want to talk a little bit about, again, I'm a social scientist, and as a social scientist, I do focus some on people and what they do, and how humanity and technology interacts, and how that affects society. And I've done this for a long time. And something I've observed in the last 20 to 25 years in the field of HPC is what I like to call the pursuit of macho flops. And this isn't meant to be facetious. It's just, and I actually didn't invent this term. It was a term invented by the vendors industry, and I don't know what company, but way back in 20, 25 years ago, the vendors would be selling their machinery to the government and to private buyers, and they would say, "Oh, so and so just is selling you macho flops. They say they got the best, flops, and they don't. It's not. My machine is better than theirs, or mine is bigger than theirs." And so what that refers to is the speed that high performance computers are measured in, and so that's floating point operations per second, or flops, and they. For as long as I can remember, this is how high-end computers, their speed is measured. And so back in the day, the earliest HPC, like the ENIAC that I mentioned, it was John von Neumann's baby, ran at something like 500 flops. Well, we've come a really long way since then. And the world's fastest machine today, it's in Japan, it's the Japanese Fugaku supercomputer, is currently #1. It's at 442 teraflops. And I have a little chart over here that kind of talks to how the speeds are measured. And right now we're on the teraflop range, and we're getting up to the petaflop range. And so the next goal is exaflops. From what I hear from my colleagues, we expect to get there in another year, maybe 2 years. And whether it's practical or usable, we'll wait to see. But that's how we measure it. But what this is based on, I've got a logo up in the top right corner here, is the top 500 list. This is the kind of standard, if you will, for how we rank the world's fastest supercomputers. And it was started by a gentleman named Jack D'Angara and his colleagues about 25 years ago. And Jack he's a colleague of mine, he's a great guy. And they needed a way to standardize and compare how these machines will perform. And and what that is, the top 500 list, they will go around, and anyone can participate. It's not mandatory, it's voluntary, but the owner of whatever computer can say, come and take a measurement of my machine, and they'll come out and they'll run a standard set of linear equations on the computer, and it will take the measurement of how it performs on the same set. And it's always the same set of problems, so it's equal, and they will go around and measure these things. And so it's become basically an industry, and it's presented every year at supercomputing, and then again at the International Supercomputing Conference in Germany in June. So the list gets updated twice a year, so the thing about this top 500 list, it's a good measure, but it's really the only thing out there. There are some alternatives to it. The Green 500, which measures supercomputers' eco imprint, I guess you could say, or how much energy it takes, which is important because these things use a lot of energy. But my point in this whole macho flops thing, and it's the subject of a book I published, and I'll show it here. In an edited collection called Feedback Loops. Andrew Garner and Ashley Hsu are the editors of it. I'll show you like that. And I've got it up on the screen anyway. But I published a chapter last fall in this book that talks about the pursuit of macho flops, the rise and fall of high performance computing. And we're kind of in a downward trend in high performance computing now, because I believe, and a lot of people in the field believe, there's been too much emphasis among the HPC community on just merely getting to #1 on this list. It's a cool thing, right? It's something to brag about. It's important. It's many nations feel like this is a sort of a what do you call it? A national a point of national pride, I think is what I'm trying to say. And that the more machines, or the most you have at the top of the list, was really a great place to be for nerdy people who like to work on this kind of thing, including myself. And so, but I feel, and having a lot of discussions with folks I've worked with over the years, that there's just been a little too much emphasis on being #1 on this machine, because you can run the top 500, the LinPack benchmark it's called. This is the linear equation set, and get a really great rating. But then when you put a real world problem on your computer, like a nuclear weapons design or something like this, it slows way down. And so it's not really designed to, the top 500 list doesn't really show, I think in all fairness, like accurately how good your machine is doing. And so it's not perfect. It's gonna need to evolve, and it is, but it's an indicator also of global changes. And this is one is the rise of China, which is something I'm concerned about, in that China as a country, before, you may not know this, before the year 2000 had no machines on this top 500 list. Today they have something like 214 last time I looked. And I'll get back to this a little later about the changing state of globalization. And this is, these are cybersecurity issues. And so these are national security issues, economic security. And so keep that in mind as we go through. And finally, there's been little substantive innovation in high performance computing architecture in the last 25 years, somewhat in interconnects and a few things. But what happens is that as we've been going forward, the hardware advances a little bit, but the software hasn't always advanced as much with it, which you need equally. We know it as the result is that HPC, as we know it, is something on the decline. I'll talk more about this a little bit too. And what does it mean if you have like the world's fastest computer on the top 500 list, or the biggest computer, and you can't do that much with it in real world problems? So keep that in mind as we go forward. And this is something that needs to be resolved. And I think we'll get resolved as we go forward. So the state of HPC, I'm going to bring us up to the present today. And as I mentioned earlier, HPC is a rarefied but still important field. And little innovation in the last 25 years. Moore's Law is coming to an end. Some of you probably know this, but Moore's Law was named after Gordon Moore, who's one of the founders of Intel Corporation. And it's not a law in the legal sense, but an observation he made that the number of transistors in a dense integrated circuit doubles about every 2 years. And that's happened pretty steadily through our recent history, but that's starting to break down at this point. And so when you can't put any more transistors on a chip, you just have problems. And then Dennard scaling has already ended. Something like this. It's a similar thing to Moore's Law, where you talks about Robert Dennard was a tech giant, and he and his colleagues observed that transistors, as they reduce in size, their power density stays constant, but that's not happening anymore. So when you get things so small, there's leakage and all these strange things happen, and it causes the chip to heat up. You have thermal runaway and increasing energy costs, and can be failure in the machine, which can be a cybersecurity issue if that machine is not operating properly. So other thing that's happened, and nobody really foresaw this, I don't think, is that in the last few decades you have a rise of big tech, and that's private industry, not government. It's what the stock market likes to call the FANG companies. That's what Facebook, Alphabet, Apple, Netflix, and Google, I believe. And it's really caught up and surpassed HPC as a driver of economic things. And there's just a lot of change has happened. And it happened so fast, we don't have time to really sit back and reflect on it. And whatever your political views, this is not a political talk, but it was, Twitter silenced President Trump after the election. It wasn't the government did that. And I just, the power they have is quite, astonishing if you sit back and think about it. What I want to add to, going back to, I showed a copy of The Innovator's Dilemma, Clay Christensen's book from it's probably 20 years old now, but it's still really great. When Clay Christensen was looking at Silicon Valley companies, he coined the notion of what he called customer capitalism as driving tech innovation today. And companies are driven now to delight their customers. They have to have the greatest and latest cool thing. And people want the new PS5. I recently read on Reddit that there's subgroups that are devoted to driving around and posting where you can find a PlayStation 5 because you can't find them right now. There's a chip shortage, which I'll get to in a little bit. And people, they don't care how the device works, but you got to have, your latest iPhone. I can't unlock my house without these things practically today. Or, people start their car with them, and it just becomes so expected. And so they don't care, but you don't care how it works. And so it's just really, that has really driven innovation in IT, and it hasn't been HPC in the government anymore. That's changed. And so all these factors I've covered here in the last few slides, Plus that cybersecurity in a sense has not really been a high priority of HPC designers. They didn't have to be in many ways. And I'll get to that in the next slide. I think, but I think that's changing. Let me go to the next slide. Okay. So cybersecurity and HPC, there's some, we'll say, unique challenges in that. And I'm not saying that HPC is going away, it's just evolving today, and I'll talk more later on that. Here, I mean, in this context, cybersecurity in terms of reliability, I've mentioned that there are exascale computing projects well underway down at Oak Ridge National Lab, and I believe there are others. If you have something, say, you have a time-sensitive, say, medical modeling problem where people's lives are at stake. You know, HPC has been supporting the COVID modeling effort, for example, in a big way, which has been good. But if you have something, say, for example, that people's lives are at stake and your reliability decreases, that can be a cybersecurity problem if the machine fails. And so generally, as you scale up on these kind of machines, the reliability decreases for some of the reasons we talked about. And then you have, you know, these extreme power requirements and leakage from your semiconductors and things. And, you know, how do you sell that? People are still trying to figure that out. And there's just a lot of different forces at work in this that are all technical and social and political. HPC as a community, again, being a social scientist, I tend to look at people and culture more than others. And I've noticed, again, studying this for 26 or so years now, there's a sort of what I call cultural exceptionalism in some of the HPC community is still present. And so it has to do with the exclusive culture that we talked about in HPC. And it's sort of rarefied, and not a lot of people do this for a living. And they tend to congregate in remote places like the national labs and in you know, scientific institutions. And I've seen that certain government HPC communities bristle when they ask Hewlett-Packard, HP, or IBM to build a certain item for them, and IBM and HP just won't do it, and they don't understand why. And I think they don't understand that they're no longer the driver of this. HP, IBM, others, Intel, they can't make as much money from the government as they can from the private sector, as we talked about a little on the last slide. And it's also, you know, it's hard. You know, people are people, and it's hard for anyone to let go of something you spent your life building, right? You know, and this is and if you're interested in this, I think one of the best books on people who design tech, it's now books from 1981, is Tracy Kitter's Soul of a New Machine. I teach this in my History of Computing and Software course at Virginia Tech, which I do every once in a while as an adjunct. It's a great read. It's a timeless book. It's about Data General. Those of you who are old enough to remember that company that went out of business at some point. But it talks a lot about the people and heroes in it and anti-heroes, and it's a great read. And I can understand people don't like change. We're all guilty of that. But change is inevitable. It's going to happen no matter what. So HPC is definitely in a state of, you know, paradigm shift, the Thomas Kuhn paradigm shift, and what Professor Christensen called the innovator's dilemma and technological change, technological revolution. And that's, again, the changing disciplinary boundaries is the rise of consumer-driven data computing is coming, and AI programming, and things like this, Internet of Things. And there's always, you know, I feel there's always opportunity to be found in this kind of change. So let's go to the next slide. So you can see my top cybersecurity and HPC. I don't know if there's anything really, you know, really too unique about it, in that HPC has some built-in physical advantages to securing itself. And so and here I'm referring to cybersecurity in terms of what I call the traditional senses as hacking and people breaking into it and such. So it's very, as I said, it's very specific, used for certain sets of problems that most people don't do. And by that in itself makes it a little more secure. It's often very customized, specialized hardware and software that very few people know how to design or work that or use it, which makes it a bit harder to access. And the components are physically close together. The data doesn't have to travel very far. Usually it's with cloud, and you have often in the government, HPCs are dependent for, say, like defense-related problems, such as modeling an aircraft carrier or something. These machines are in closed settings on a military base or closed or behind a fence, and so they're and foreign nationals don't have access to them, and so they're secure in that sense. And again, the language too. So many still run programs like Fortran. They're programmed in Fortran. Younger people don't tend to use those things. So it's, there's it's not necessarily a big problem. So I'm going to finish up on my last couple slides because I've only got a few minutes left here. Let me go to the next. I think I have 2 left. Okay, so I want to make some recommendations to finish off. So we have to view extreme scale security at a macro and a micro level. At national perspective, you may see that President Biden back in February had put out an executive order on America's supply chains because there was a chip shortage. And the chip supply chain is global. That's a little scary. Intel made an announcement in the wake of that. They're going to onshore production. That's great. I think it's great for national security and cybersecurity. Reinvigorate the Made in America idea. They're going to, Intel's supposed to build 2 new fabs, semiconductor fabs in Arizona. And post-Moore's architecture, as we move to UbiComp, that's like taking data computing over here and HPC and bringing them together. It's more affordable to do. It'll present opportunities. And definitely need to focus on things like STEM, technical STEM education at the elementary level. And we need to be thinking big about this. So I've got a couple minutes left here, and we need to design for data, not processor performance, not macho flops, not being #1 on the top 500 list, and hire more cybersecurity specialists, probably on a per project basis. And I like to say, odds are another 40 years, we're not going to recognize HPC as we do now. It's just, it's evolved. People tend to accept what technology is available to them, and they will. And I think we're going to see a lot of very interesting things in the horizon as things like AI computing mature, which is still not mature, but we're going to have a secure future and be machines that can learn things like this. And my last slide, where to go from here. We need to include interdisciplinary teams when we do these research and solutions, and not just engineers and technologists, but social scientists and people who understand things like language and culture. Diversity is a big thing. So when moving forward, people from diverse backgrounds have unique insights into things, to rethink the HPC workforce, and talk about and really support STEM education. This is a big important thing of mine. So that's all I've got today. I'm here to answer questions when this runs live, and I appreciate your spending a little time with me this afternoon. And thank you for your attention. If you want to get in touch with me, I have an email here you can see. I'm always happy to chat. So thank you for your time today. I've had a good time speaking with you.